These are going to be our notes on the chain rule. So far, what we have learned is that we know how to take derivatives or how to differentiate constants, functions times constants, sum and difference of functions. We can do multiplication and division of functions, and our trig functions. But what we don't know how to differentiate yet are composite functions, meaning one function within another function. So for example, if we want to differentiate f of x equals the square root of x, we know how to do that. We treat the radical as a power of 1/2, and then we just use power rule. The derivative of that function would be 1/2 times x raised to the negative 1/2. But what we don't know how to take the derivative of is a square root function that has another function substituted under the radical instead of just x. The derivative of a composite function, f composed g, is the product of the derivatives of f and g. So here's what the chain rule states. If y, which is a function of u, is a differentiable function of u, and u equals g of x is a differentiable function of x, then y, which is equal to the composition f of g of x, is a differentiable function, and the derivative of y with respect to x is equal to the derivative of y with respect to u times the derivative of u with respect to x. That's one way to write it. The other way to write it is that the derivative of d dx of f of g of x is equal to the derivative of f evaluated at g of x times g prime of x, or the derivative of g at x. So let's see if we can explain what some of this means before we actually do some examples. So let's talk about the first notation. That's this one. All of this is just a repeat from the previous slide, and this is the first notation we discussed. dy dx equals dy du times du dx. So what this says is, if you notice, your y is a function of u, but u is g of x. That's how this composition function y equals f of g of x is coming about. This u inside the f of u is an entire function itself. So when you want to find dy dx, you can't just take the derivative of f of u, because that doesn't give you dy dx. It will give you dy du. So that's what you find first. You take dy du, which is the derivative of the function f with respect to u, times the derivative of this u function with respect to x. U equals g of x. You take its derivative with respect to x. So in other words, let's talk about these u's and what they mean. If you have a function y equals 1 over x plus 1, what you have is a composition function. You have x plus 1 as an inside part of that function, and then you have 1 over x plus 1 as an outside part of that function. So what we do is we say u is the inside, the x plus 1, and y is what you get when you take 1 divided by u. If you have y equals sine of 2x, then what we mean by u is the inside part. U is 2x, and y is sine u. So what we're trying to do is differentiate between the inside and the outside functions. But if you say u equals 2x, you can't then say y equals sine x, because it doesn't. It's sine of 2x. So you have to basically use what's called a dummy variable inside this function to indicate it doesn't have x's in it. It's got this entire function in it. If you have a function y equals the square root of 3x squared minus x plus 1, then u, your inside function, is what's under your radical. It's 3x squared minus x plus 1. And y is the square root of that inside function. If you have y equals tan squared x, now please keep in mind, tan squared x means you have the tangent of x squared. So your inside function is tan x, and your outside function is that tan x squared, or the u squared. As opposed to, when we write tan of x squared, that means the only thing getting squared is the x value. X is your angle input. The angle gets squared and then you take the tangent, as opposed to the one above it, which says you input the angle into the tangent function and square the result. So there's a big difference between these two. But also there's a big difference between the inside and the outside. That means your inside function this time is your x squared, and your outside function is the tangent function. So it's the tangent of the inside function. So that's a little bit of an explanation of that notation. We haven't actually taken any derivatives yet. We're just trying to understand what the notation says. Let's look at the second notation, which again, this is the same setup as the first slide that explains what the chain rule says, but now I have the second notation here. d dx of f of g of x equals f prime of g of x times g prime of x. So it says the exact same thing, just in different notation. This one's a little bit easier to explain in words. It says you're taking the derivative of the outer function, f being the outside function. So here's the derivative of the outer function, but you're evaluating it at the inner function. You're holding that inner function as is. You are not touching the inside function. And then you're multiplying that times the derivative of the inside function. So if we look at some of the same examples, if you have y equals the square root of 3x squared minus x plus 1, your inner function is 3x squared minus x plus 1, and your outer function is still that square root. But this is a lot harder to notate nicely. You shouldn't really just write square root with nothing under it. So that's why we also have that first notation. It's more mathematically precise to be able to write out your chain rule. But the idea is the same no matter which notation you're using. So if y is tan squared x, which again is the tangent of x squared, your inner function is tan x, and your outer function is that something squared. If you have y equals tan of x squared, then your inner function is x squared, and your outer function is the tangent of the inner function. So let's look at an example. We'll go back to the square root one that we've discussed, and we'll actually do it using both notations. If you do this using the first notation, as we mentioned, we let u equal 3x squared minus x plus 1, and we let y equal the square root of u. That gives us this function that we're trying to take the derivative of. And remember, using first notation, in order to find dy dx, we need dy du times du dx. So dy du is the derivative of y with respect to u. Remember, this is just u to the 1/2, so that will be 1/2 times u raised to the negative 1/2 times du dx, which is the derivative of u with respect to x. That's this function. The derivative of u with respect to x is the derivative of 3x squared, which is 6x, times the derivative of negative x, which is negative 1, excuse me, not times, just minus 1, and then the derivative of 1 is going to be 0. So the problem with this is we are using this to find dy dx, which means our independent variable on that right side should be x, which in the 6x minus 1 is fine. The problem is I still have u's here. So what I need to do is put u back in terms of x. So I would have 1/2 times, instead of u, I write 3x squared minus x plus 1, that's still raised to the negative 1/2, times 6x minus 1. So when we clean up the notation just a little bit, keep in mind negative exponents move functions to the denominator. In our numerator, we'll have 6x minus 1. In the denominator, we'll have the 2 from the fraction of 1/2, and then the 3x squared minus x plus 1 will move to the denominator to make this a positive 1/2, and then 1/2 just changes it back to a square root. So that's 3x squared minus x plus 1. And that's our derivative using the first notation. Let's do it again using the second notation. For the second notation, our inside function was 3x squared minus x plus 1, and our outside function was the square root of that. So the second notation says that d dx of f of x equals f prime of g of x times g prime of x. So in other words, we need the derivative of that outside function, which we just said is the square root. So f prime of x will be, the square root is the outside function, so there's your 1/2 times, and then you'll have a new power of negative 1/2. You need to evaluate the derivative of the outside function at the inside function. Don't touch that inside function. It stays 3x squared minus x plus 1. And then we multiply that times the derivative of g at x, or g prime of x, g being your inside function. So the derivative of your inside function is, again, 6x minus 1. And if you notice, I can simplify this again, but if you notice, it's the exact same thing I got using the first notation. And it really doesn't matter to me which of the two notations you use or which you prefer. I believe you are more likely to see the second notation when you look at your book or when you look at solutions manuals. But the first notation is going to be especially helpful when we start looking at applications. But at this point in time, you're free to use whatever you're most comfortable using. So when we combine the chain rule with the power rule, what we get is the general power rule. It tells us that if n is any real number and u equals g of x is differentiable, then when you go to take the derivative with respect to x of u to the n, here comes the power rule. You drop the n down as a coefficient. You don't touch that inside function. You leave it just u the way it is, raise it to the new power, which is exactly 1 less than the original power, and then multiply times the derivative of the inside function. If you want it in the other notation, that says that d dx of g of x to the n is n, drop down the n as a coefficient, hold g of x as is, raise it to the new power, times the derivative of g of x. Let's look at some examples. We're going to find the derivative of f of x equals 3x minus 2x to the fifth, all raised to the third power. So your inside function is this 3x minus 2x to the fifth. The outside function is the cubing function. So when we go to take the derivative, df dx, or f prime at x, either one's great, we need to take the derivative of the outside function. So that's drop the 3 down as a coefficient, and then we're going to raise it to a new power of 2. But what goes in here is the original inside function. You don't touch that inside function. But now you need to multiply times the derivative of the inside function. The derivative of 3x is 3, and the derivative of 2x to the fifth is 10x to the fourth. So that's its derivative. If we want to differentiate g of t equals negative 7 divided by 2t minus 3 squared. We actually can go about this 2 different ways. If your inclination is to use quotient rule, that will work out. Let me do it that way first. If we use quotient rule, then dg dt, or g prime of t, either one, we will have the denominator, 2t minus 3 squared, times the derivative of the numerator. Well, the derivative of negative 7 is 0 because it's a constant, minus the numerator, negative 7, times the derivative of the denominator. And this is where chain rule comes in. The squaring function is the outside function, so we drop the 2 down as a coefficient. We don't touch that inside function, and we raise it to the new power of 1. And then we multiply that times the derivative of the inside function. The derivative of 2t is 2, and the derivative of 3 is 0. And then we put that all over the denominator squared. So that'll be 2t minus 3 to the fourth power. So when we clean that up, notice the first term gets multiplied by 0. So it becomes 0. My second term becomes positive, and I get 7 times 2 times 2. That'll be 28 times 2t minus 3 to the first power, so I'm just not going to write that, over 2t minus 3 to the fourth power, and they're nice, which means those are nicely going to cancel, and I get 28 over 2t minus 3 to the third power. That is one way of going about this. The other way of going about this is to rewrite this first, is to, instead of thinking of this as negative 7 divided by 2t minus 3 squared, think of it as multiplication. of taking negative 7 times 2t minus 3. But if you're going to move a factor from the denominator up to the numerator, that positive exponent is now going to become negative. These are equivalent to each other. And now what you can do is just use power rule and chain rule. So then g prime of t will be negative 7 times that negative 2, because this is the chain rule. We drop the negative 2 as a coefficient, leave the 2t minus 3 as is, and raise it to the new power of negative 2 minus 1, which is negative 3, times the derivative of the inside function. And the derivative of 2t minus 3 is 2. So in other words, there's the negative times the negative for positive. That is 7 times 2 times 2 for 28 times 2t minus 3 to the negative 3, which means you get 28 over 2t minus 3 cubed. Same thing either way. And now that you have chain rule, you're going to be able to avoid quotient rule a lot more often than you would have been able to without it. Let's look at another example. We're going to differentiate y equals the tangent of 3 theta. So in this example, 3 theta is your inside function, tangent is your outside function. So when you go to find dy d theta or y prime of theta, either one's great, you need the derivative of the outside function, so that's your tangent function. Remember, the derivative of tan x is secant squared x. So we'll have secant squared, but we don't touch the inside function. We leave the 3 theta as is. So this is the derivative of the outside, evaluated at the inside function. But now I need to multiply times the derivative of the inside function. And the derivative with respect to theta of 3 theta is just 3. And in general, when I write these, I like to put the constant out front, because otherwise I run the risk that if I'm not paying attention, I might try to multiply the 3 theta times the 3 and make that 9 theta, and that's definitely not legal. Okay, let's take a look at the derivative of f of x equals cosine squared x. So we need to be able to identify the inside function and the outside function. So again, keep in mind, this is the cosine of x squared, which means the inside function is cosine x, the outside function is your squaring function. So the derivative of f at x, we take care of the outside function first. We bring down the 2 as a coefficient. Don't touch that inside function. Raise it to a new power, which is 1 in this case. You don't have to write the 1, but I'll go ahead and do it for now. We then need to multiply times the derivative of the inside function, and the derivative of cosine x is negative sine x. So this derivative is negative 2 cosine of x times sine of x. Okay. Compare that to the next example. If we have f of x equals cosine of x squared, and again, that means cosine of x squared. So now the inside and the outside function have switched in comparison to part A. The inside function is x squared, the outside function is the cosine function. So when we go to find the derivative, we need the derivative of cosine first. The derivative of cosine is the negative sine. Don't touch the inside function, times the derivative of the inside function, and the derivative of x squared is 2x. So in other words, this is negative 2x sine of x squared. So notice the derivatives are distinctly different depending on which is an inside function and which is the outside function. Let's take a look at this one. If we wanted to find the derivative of h of u equals u cubed minus 1 raised to the 100 power. Now that we have chain rule, that's not actually too bad. The derivative of h at u, the outside function is the power of 100, and the inside function is u cubed minus 1. So we take the derivative of the outside function, which is dropping the 100 as a coefficient, and having a new power of 99, 1 less than 100. Do not touch the inside function, and then multiply times the derivative of the inside function. And the derivative of u cubed is 3u squared, and the derivative of 1 is 0. And you can just leave it like that. Let's also find DDR of 3r minus a divided by r squared plus t raised to the third power. And I have purposely included a lot of extra variables in this because it's important to keep an eye on which letters represent variables and which letters represent constants. Since this derivative is with respect to r, the only variable in here is r. So as far as we are concerned, a and t both represent constants. So when we find DDR of this function, we have an outside function of a cubing function, and then the 3r minus a over r squared plus t is your inside function. So we will take the derivative of the outside function first. Drop the 3 down. Don't touch your inside function. Raise it to the new power of 3 minus 1, which is 2. Now you need to multiply times the derivative of the inside function. This is a quotient rule. We're going to have to use quotient rule to take the derivative of the inside. So that means we need the denominator, r squared plus t, times the derivative of the numerator. So again, keep in mind, r is your variable. So the derivative of 3r is 3, and the derivative of a is 0. So that's the derivative of your numerator, minus your numerator, 3r minus a, times the derivative of your numerator. The derivative of r squared with respect to r is 2r, and the derivative of t with respect to r is 0. All over the denominator squared. Okay. So let's see if we can get a little bit of simplification going on with this. Usually with these we can try and get some things to cancel if it's possible. If not, we'll just make it look prettier at the very least. So in my numerator I have the 3 from the constant. I'm going to split up this 3r minus a over r squared plus t squared into a squaring of my numerator and a squaring of my denominator, r squared plus t squared. The reason I'm going to do that is I see I have another r squared plus t over here, and I'm probably going to be able to put those together by multiplying them. In the numerator of this quotient rule, I will have, this is times, 3r squared plus 3t. Let's see, I'll distribute the 2r to both of these terms and distribute the negative through. So that's going to be negative 6r squared plus 2ar. All over r squared plus t quantity squared. So when we clean it up a little bit, we'll have 3 times 3r minus a squared. I'm going to go ahead and multiply these two fractions together as well. In my numerator, I have 3r squared minus 6r squared. That'll give me a negative 3r squared. Plus 3t won't combine with anything. Plus 2ar doesn't combine with anything. All over, when I multiply my denominators, I'm going to get r squared plus t to the 4th power. And it looks like that's going to be about as nice as I can get this. So that's my derivative. Let's take a look at another example. Okay, let's take a look at this derivative. We're looking to find the derivative of f of t equals e to the at times sine of bt. So when we look at this function, we want to try to decide what kind of rules we're going to need to take the derivative. I notice a couple of things. One, I see a product going on. This is e to the at times sine of bt. That tells me that I'm going to be using product rule in order to take this derivative. But in addition to that, I notice that I don't just have the variable up in the exponent of my exponential. T is my variable because this is f of t. So I have an entire function sitting up here, that function being a times t. Also, inside my trig function, I don't just have t, I have bt. So both of those derivatives are actually going to involve chain rule as well. So let's start by writing out my product rule. So the derivative with respect to t f prime of t, also known as df dt. I'm going to do the derivative of the first function first. So the derivative of e to the at is e to the at, but times the derivative of at. So for the moment, I'm going to write that as at prime, meaning I'm going to take the derivative of this in just a bit. Now that's going to be, by product rule, that's the derivative of the first function. I need to multiply that times the second function. So that's times the sine of bt, as is. And then plus, I need the first function as is, so that's e to the at, times the derivative of the second function. Well, the derivative of sine bt is going to be cosine bt, do not touch that inside function, times the derivative of the inside function, so times bt prime, meaning I'm about to take the derivative of that. So once I've got the product rule written out, really all I have left to do is take the derivative of at and take the derivative of bt. Keep in mind that our independent variable is t. So when you go to take the derivative of a times t, it would be like taking the derivative of, let's say, 6t or 10t. A acts as a constant. So when you take the derivative of a constant times the linear, you just get the constant itself. So the derivative of at is a. So I'm going to write a e to the at sine of bt. And then for my second term, I'll have e to the at times cosine of bt. I haven't done anything with that yet. And then the derivative of bt with respect to t is again that constant b, which I'll go ahead and choose to write out front here so I don't get confused. And that's the derivative. We're going to differentiate f of x equals the sine of the cosine of the tangent of x. So the first thing to keep in mind about this function is that this is not multiplication of anything. There's no multiplication going on in this function. If we meant this to be multiplication, we would have written sine x times cosine x times tangent x. You would see x as an input into each one of the three trig functions. Notice you don't have that. This is actually a composition function. It is an input of x put into a tangent function. The result then put into a cosine function, and the result of that then put into a sine function. So composition means we're about to use chain rule for this, but it's actually not just one composition. This is a function within a function within a function. Okay? So we're going to have to be careful about taking our derivative. So we always start with the outside function. So we start with the derivative of sine. The derivative of sine x is cosine x. So this derivative will be cosine. Now, we don't touch that inside function. So we leave this as cosine of tangent of x. Okay? So that's just the derivative of the outside function evaluated at the inside function. We then need to multiply times the derivative of the inside function. Let me color code this a little bit. I need to multiply times the derivative of the inside function, which is now cosine of tangent of x. So its outside function is cosine. The derivative of cosine is negative sine, but you don't touch the inside function. You leave it evaluated at the tangent of x. But now that's the derivative of its outside function evaluated at its inside function. But we now have another inside function, which means we need to multiply times the derivative of its inside function. So the derivative of tangent x is secant squared x. So putting it all together, we have the cosine of the tangent of x times, and there's a negative here, so I'm actually going to put the negative out front. You don't have to, but I'm going to put it there. Times the sine of tangent of x times secant squared x. So it's actually a chain rule within a chain rule. Let's take a look at another one. We're going to differentiate y equals the square root of the secant of t cubed. So keep in mind that that is the secant of t cubed, and that function is raised to the 1/2 power. So believe it or not, this is also a chain rule within a chain rule, because I have an outside function of the radical, the power of 1/2. My next inside function is going to be a secant function, but then it has an inside function of t cubed. So let's take a look at the derivative. The derivative will be dy dt. Okay. We take the derivative of the outermost function first. That's my power of 1/2. So we drop the 1/2. We will have a new power of negative 1/2, and we don't touch our inside function. We have the secant of t cubed. We then need to multiply times the derivative of secant of t cubed, which has an outside function of secant. So remember, the derivative of secant x is secant x tangent x. So the derivative of secant of t cubed is going to be secant t cubed tangent t cubed. Okay, just t cubes in place of x, but that is itself an inside function, which means we then need to multiply times the derivative of that inside function, the inside function being your t cubed. So times the derivative of t cubed, which is 3t squared. So putting all of that together, we have a 2 in our denominator. This secant of t cubed is to a negative 1/2, so in order to make that positive, we'll put it down in the denominator and then change it back to a square root. So this is the secant of t cubed. This secant of t cubed times tangent of t cubed, that's all positive, so that goes up here. Secant of t cubed tangent of t cubed, and then it's getting multiplied times 3t squared. But again, I'm going to go ahead and throw that out front so that I'm not confused as to whether or not I can put that inside my trig functions, which I can't. So that's the derivative. So those are some basic examples of how we're going to use the chain rule.